Let's talk about section 5.3, which is all about our exponential and logarithmic equations. Now, everything that we learned in 5.2 is very important to keep in mind. So as we move into this, we are going to still use all of that information, but remind yourself that we're going to take this to another level, and we're actually going to learn how to solve exponentials equations by maybe switching it into a logarithm. We're also going to learn another formula, which will be our change of base formula. We're going to solve those exponential equations by using those properties of those logarithms. And then we're going to solve some logarithmic equations as well. Okay. So we'll start by just solving exponential equations using a logarithm form. There's kind of a four-step process. So step one is it's got to start off an exponential for these steps to work in the first place. But once we have it, we're going to rewrite the equation with the term containing the exponent by itself on one side of the equation. Now, what we mean by that, and this is where I guess some people get a little bit confused. If I have basically, say, let's take a look at like 15 equals 7 times e to the power of 2x here, okay? One, I know this is an exponential equation because x happens to be in the exponent. That's what makes it an exponential equation. Step one says rewrite the equation with the term containing the exponent by itself. Now, yeah, this term right now has the one with the exponent, but what I mean is basically this 7 has to go. Okay, that's what step number one is actually referring to, is that I need to get that 7 to the other side. Now you're going to rewrite by using maybe addition, subtraction, multiplication, and division. In my case here, I would say I would divide by 7. Okay, if it didn't have the 7 like there, it had maybe, if it looked like, say, it had like a plus, I don't know, 210. Then I would actually take that 210 and subtract it to the other side. So this is when we say rewrite, it's in very general terms, but basically get whatever the base is with the exponent by itself, okay? So get that term by itself. So you're going to rewrite the equation where that term is by itself, divide by any number that's in front of that base, okay? So that's where that divide comes in. And then step 3 is actually where the big amount of work comes from, okay? Now, with that being said, okay, step 3 says change the new equation to a logarithmic. Now, this is where you're going to have to keep in mind. This part right here, okay, is where we're going to take what we learned in previous sections, going from something that is an exponent right here into a logarithmic. So it now becomes log base b of y equals x. Okay, once you've changed it into logarithmic form, now we can actually solve for whatever that variable might be. So let's take a look at this, okay? I am going to kind of give a little bit of warning, okay? Before we jump into the solve part itself, I do need to kind of remind you the difference between what is an approximated answer and an exact answer. And I'm going to ask you to really make sure that you're reading directions very closely here. Some questions are going to ask you to round or approximate. If they do not use the word round or approximate, you are giving an exact answer, which means basically an answer that has no decimals. Exact answers can basically be the expression where you haven't plugged it into the calculator. Okay, if it says approximated or rounded, then that means you plugged it into the calculator to do a little bit of rounding. Okay, so keep that in mind as you're working on the problems. Approximated answers are normally given when we talk about word problems, but in general terms, we do try to keep them with exact answers. So let's solve the following equation. 3,000 equals 150 times 10 to the power of 4t. 4t by converting it to a logarithmic form. Okay, now please understand that when most of these problems, it's just going to say solve and then give you this equation here. So it doesn't actually normally say anything beyond that. So it's just going to say solve and it's just going to have the equation. Okay, and this is where we're going to have to use our math toolboxes and remind myself of all the different things that I learned when dealing with math. Okay, and I have to go, okay, first of all, what type of problem is it? And the first thing I notice is this part right here. Where is that exponent? That's always what I'm looking for before I jump in on any problem. Okay. Find the exponent first. Okay. Not the exponent, sorry, the variable. And where is that variable located is actually going to kind of give me a lot of information on how to solve. In our case here, my variable's stuck up here in the exponent, and that's why I'm going to know, okay, since it's stuck in the exponent, I want to convert stuff to logs because we have the rule where if we change things from exponential equations into log equations, basically a log equals the exponent. So that's kind of where that step comes in. So we're going to start by going ahead and dividing both sides by 150 because the term that has the variable is up here. So now I need to divide by 150. What that does is that's going to cancel out the 150 over here. Okay. Now go ahead and take a second and make sure that you can actually do this division. Okay. If it doesn't divide nicely, leave it as a crazy looking fraction. Okay. If it divides nicely, go ahead and divide it out and make it into that like 20. Okay. And we're left with 10 to the power of 4t. Now, again, I can't just say divide by 10 because no. 10 is the base of our exponent there. Okay. So in our case here, this is where we switch it. So we're going to say this is now log base 10 of, cross that equal sign. Okay, so we have log base 10 of 20 equals 4t. Now, we've now gotten t out of being an exponent. Now, log base 10, I want to remind myself, I can actually plug log base 10 into the calculator, but don't plug it in until you fully solved out for t. So the last step I need to do is I need to actually get rid of that 4. So to get rid of that 4, I need to just divide by 4. Okay. And ladies and gentlemen, that's going to give us our final answer there. Okay. So when we do all that out, we end up with that nice, lovely t equals log of 20 over 4. Now you'll notice I kind of let that base 10 disappear. And anytime that you hit the tutor button, or ask for a bit of help, a lot of times when you see people write it, they're not going to write log base 10. If you need to write log base 10, you write it down, okay? So we start by dividing both sides by 150 there. Got that 20 equals 10 to the power of 4t. We rewrote it as a logarithm. And again, there is, kind of small here, but it is there, is that base 10. It's just, again, we don't normally write that base 10. We just let it disappear when it is in a base 10 because that's our common log. And so log of 20 over 4. Now this right here, this is what we would call that exact answer. And this over here is my approximated answer. So if it didn't say to round, you're going to leave it as log of 20 over 4. And I know there's a couple of homework questions that you're going to do that with. Now for the approximation, that means I'm going to have to plug it in the calculator. And again, as you plug that into the calculator, so log, that's this button here. Again, that's the base 10 log. So I don't have to do anything magical. And 20, make sure you close the parentheses here. It's very important. And then divide by 4. For those of y'all that have the option to make it look like a fraction, okay, you can always make it look like that fraction. Again, make sure you close the parentheses there. And you'll still get the exact same answer. So whether you have a TI-83 or if you have a TI-84 with the option to make it look like a fraction, you'll still get that same answer. Be sure that if it does say to round, make sure it looks, where are we rounding to? It's anywhere between 3 to 5 decimal places on the rounding. Okay. Now we could have also solved this one graphically. So previously when we did these before, we would have just plugged in the 3,000. Ooh, I got a lot of stuff in there, so let me clear that out. Previously before, we're going to put in that 3,000. And then in the y sub 2, I would just say that 150 times 10 to the power of 4. And again, we don't put t in the calculator, so we're just going to change it to an x. Okay. And I can do it this way. The problem with this is basically when I graph it, I may not see everything. I have to adjust my window. I have to remind myself, oh, well, I plugged in 3,000. So I need this to be higher than 3,000 in the first place. So 3,500 would be good. Okay, now I can see where they cross. Okay, and that's where I would do that whole second trace, number 5. And again, I'm going to kind of first curve, second curve, and then my guess. Okay. Now, here is the biggest problem with the guessing, just so you guys can have an idea. You'll see how here is where my guess right now is. Even if I switch to another, like, it just really doesn't get super close. And the only way to get super, super close is to basically make a lot of adjustments like I did here on the viewing window. So as you can see on the one that I have here, it's that viewing window is definitely changed. But no matter what, I still get the same answer as this. And again, your first couple of digits will be the same. You don't have to be perfectly on it on your guess, but as long as you're somewhat close, you're going to get the right answer. Okay, so let's try another problem. So let's prove that the time it takes for an investment to double is its value of t equals the natural log of 2 over our rate. And if that's basically if the interest rate is r, compounded continuously. So remind yourself, we learned back previously about this keyword compound continuously. It would have been early on in chapter 5. So early on in chapter 5, we learned about compound continuously. And anytime we talk about compound continuously, we were meant to think about this formula here, S equals P times E to the RT. Okay, now do remind yourself that this formula will come back later. So it's, again, something that shows up multiple times, which is why we want to keep it in mind. Okay. And previously, when I was using these to solve, we really couldn't solve anything other than actually by doing it, with the calculator. Now we're going to do it by hand. So remind yourself that, again, prove that the time it takes for investment to double in value. Now I'm going to do this very general terms. So we know that we start with P because P is always that starting value. Remind yourself that's what this was. So if I double, that should be 2 times P. Okay, so realistically, we're looking at first, this S becomes 2P. So we have P times E to the RT equals 2P. Okay, so the rule says basically we've got the term by itself, so let's divide both sides by P. Okay, divide both sides by P. Woohoo. That was kind of that step. We rewrote it. That's the first thing we did. So step 2 was divide by that coefficient, which the coefficient in our case here is P. So that leaves me with 2 equals E to the RT. So now step 3 was basically convert to a logarithm. All right, so when we convert that to a logarithm, this is going to be log base E of, again, cross the equal sign, of 2 equals, over back to get the exponent, RT. Now again, do we write log base E? No, log base E is actually natural log. So instead of writing log base E, I'm just going to have the natural log of 2 equals RT. And last thing is solve for T. So if this says R times T, the opposite of multiplication is division. And we basically now have T equals the natural log of 2 divided by R, which we just proved right there. Okay, now I'm going to erase my ink. So if you need to pause, go ahead and pause, but I'm going to erase the ink so I can show it in a nice, better format that's written out. Okay, but again, just remind yourselves what a lot of people make a mistake on is this part right here. Is they want to type in log base E and you might get something back that says it's not fully simplified. And it's just because we don't write log base E, we switch it to that natural log. Okay. Okay, so we've just proven that this is actually true. So that's super cool that we've actually proven that this is actually true. So when do I actually use this? Well, the only time that this formula here can be used is when I'm asking you how long it takes something to double in value. Okay, and we know that it's compound continuous. So if we talk about something being compounded continuous and we want to know its time, the time it takes to double its value, then I can use that formula, okay? And that formula is super, super helpful. So keep that in mind and maybe put it aside, okay? But when in doubt, we can always use this formula here and then just do the long route of solving for it. You'll end up getting something similar to this when you simplify it all down. So let's try this out. So let's look also for those keywords here. So suppose you have $2,500. It's invested in an account earning 6% annual interest compounded continuously. Keyword. How long will it take for the amount to grow? How long will it take the amount to grow to 5,000? Now, that doesn't necessarily say the time it takes to double, but what it does say is I'm starting with 2,500 and then I want to know it to grow to 5,000. Now, just looking at those numbers right there, I go, wait a second, 2,500 to 5,000 is doubling. So ladies and gentlemen, I've got all the keywords I need. I can actually use t equals the natural log of 2 over r. Now, again, you can still take the long route and use that, the fact that I have compounded continuous. I can still use that formula, but I do want to kind of just, if I see those keywords, I definitely would prefer less work. Okay, so it's totally fine that you can, and that's perfectly fine. If you want to go the long route, there's nothing stopping you. Okay, so if you want to compound continuous and we can go this route, we totally can. All right, but because I saw my lovely key things, I was like, oh, I can bypass this formula completely and go straight to this. Again, this only works if you're looking for double the amount. So the time for double the amount. And again, it has to be with compound continuously. If it's not with compound continuously, you cannot use this formula. Okay. Now our rate was 6%. So again, with that beautiful 6% there, change it to a decimal. So I'm literally looking at the natural log of 2 divided by 0.06. And that's it. That's all I have to do. I'm done. Now, again, we could have gone a different route with it. We could have used the calculator and that would have worked just as well. But just be aware that, again, pick which method is going to work best for you. But again, if I find those keywords, I would definitely use this formula instead. Okay, let me add another formula because you're going to need it, especially for those of y'all that have a TI-83. Those of y'all that have a TI-83, you kind of can't do log base in that calculator. So you would definitely need this formula, which is called the change of base formula. The change of base formula called for basically a way to rewrite logarithms so they can be expressed in terms of log base 10 or e. And the reason why we want them technically in log base 10 or e is, let me pull back up the calculator again. So when you look at the calculator, there's really only 2 buttons that have log. Okay. Now, again, those of y'all that have a TI-83, this is your only option, is you kind of need the change of base formula. Those of y'all that have a TI-84, so again, you have a TI-84, you have the ability to use the log base. But again, this is only because your calculator is a higher power calculator. The lower the calculator's power, the ability for it to do a log base is actually not there. Okay, so keep that in mind. That's why this is kind of important to see. So with this formula itself, let me go ahead and put a couple of stars by something. Pick one. I don't care which one. For those of y'all that are going into calculus, I recommend this one to keep memorized. For those of y'all just in general, you might want to memorize this. I know this, when you look up here, this is what the formula says. Realistically, memorize one of these instead, or at least have one of these written down instead. Don't do this. Okay. And the reason why I say don't do this is just because it's really confusing when you have log base A, and realistically, you really only want it to be log or natural log because those are the only ones that you can plug in the calculator. Okay. So the way it actually works is that if you have, say, a log with some base other than 10 or E, because we don't have those in the calculator, I can rewrite this as the log given my base that I choose of the inside divided by the log of the same base of the top one that I choose over the original base. Okay. So in our case here, it would literally be, so if I'm choosing base 10, it would be the log of X divided by the log of A. If I choose log base C, it'd be the natural log of X over the natural log of A. Okay, so again, take your pick which one of these that you would like. Again, if you are going to head towards the calculus route, I recommend this one instead. But again, either one of them, both of them come out the same. So if you prefer writing log versus ln, then go this route. Okay, so let's evaluate and let's actually use the change of base formula. So we're going to evaluate log base 8 of 124, and we're going to use the change of base formula, actually use it. Okay. So again, right here is where I go, okay, well, I can choose either 10 or E, take your pick. So if I choose 10, that's going to be the log over log. And again, it's log of the inside over log of the base. The base is always on the bottom. Okay. In general, if I chose, say, E, that would have been the natural log over natural log. And again, it's always of the inside over the base. What's super cool about that is, again, I can use my calculator here to really kind of help me out. Okay. So I'm going to use my calculator and I'm going to say the log of 124, close those parentheses and divide by the log of 8. Again, it has to be log and log, or it has to be natural log and natural log. Okay, let me also do it with the natural log. Let me show you that it is actually exactly the same answer. So no matter which one you use, you should get the exact same answer. Now, again, those of y'all that have the ability, again, not everybody has this ability, so please keep that in mind. Those of y'all that have a higher power calculator that can do a log base, you can actually use the log base feature. And when you do that, you get that same answer as if I was using the change of base formula, which makes that really kind of cool. Okay. Okay. Now, again, when we do that, that is an approximation, so keep that in mind. Oh, I went too far. Dang. Okay. Now, why do we need this? Well, this is actually allows you to put this in the graphing calculator. So I want to just kind of show you how to put this in the graphing calculator, especially for my TI-83ers. Again, those of you who are a TI-84, you've got this log base feature, but not everybody does. So for those of y'all, again, this is what we're graphing. Oh, sorry. Let me pull it over to the side so you can see it. So this is what we're graphing. And again, for those that have, I'll start off with my TI-84s. My TI-84s go into Y equals, and then you're going to hit the math button, arrow up to the log base, and then plug in there. Okay, so you're good to go. Those that have my TI-83s, you don't have the log base. So this is, how do I actually plug this in the graphing calculator? This is where that change of base is going to come in. And again, take your pick, whether it was a logs or natural logs. So I could have taken the natural log of the inside, close the parentheses, divided by the natural log of the base, which my base is 3. Okay, or common log, your choice there. Okay, and let me go ahead and zoom 6 it. So back to the standard window. And again, you'll see they're the exact same thing. Okay, and they're both going to look like that. Again, it doesn't really matter which version you use. Those of y'all that have that really pretty change of base, then that's great, but not everybody has that. Okay, so you kind of want to just change whatever this is into either base 10 or the natural log. It's up to you, but keep that in mind. Oh, there's a typo. Dang it. I knew I was missing one. Ignore that. That one's natural log. I wrote it right over here. Okay. So just keep that in mind. It's your choice. I'm not going to say which way you have to go with it, but just kind of keep that in mind as you're working these problems. If you have a TI-83, you kind of want to keep that change of base rule. And the way I write it down, just to kind of keep it in mind for my change of base, is log of base of, and then you can put any letter here. It doesn't matter. And then pick which one you picked. I like natural logs better, so I like to write natural log of the inside over the natural log of the base. If you like the common log one, common log. Again, I lean more towards the natural log because I went through the calculus route. And again, in calculus, we use a lot of natural logs, so that's why. Okay. Let's look at another problem. So if $10,000 is invested for T years at 10% compounded annually, the future value is given by the following formula. Now, in how many years will the investment grow to $45,950? Okay, now they've already given me a formula. So that is really, really helpful. Okay, everybody see that beautiful formula? But remember, S basically stands for the future value. And they said, in how many years, y'all, that right there is time. That's T. That's what we're looking for. Will grow to this. Again, this is investment grow to. Grow to means future value, right? So right away, as I'm kind of looking through this, I'm going, okay, well, if this is the formula, I've now basically taken this 10,000 times 1.10 to the power of t, and I'm going to let it equal that 45,950. Okay, now that I've got you set up, if you want to go ahead and solve it, go ahead and pause the video here and you try it. If not, you can follow along with me. And again, we're going to take this step by step. Okay. So if you've paused, welcome back, and let's make sure that you did the steps correctly. Again, as you're working these problems, it's really helpful to write down the steps as you work through them. Okay, and as you guys are watching these videos, I highly strongly recommend, and I know that was a lot of like big words there at the same time, highly strongly recommend write down stuff. It's really helpful. It does help with your memory actually writing down things. So we found our term that has our variable in it. We're going to leave that term alone. And again, there's nothing being added or subtracted, so we're good there. But now we need to get rid of that 10,000. So we're going to start by dividing. And again, what I do to one side, I do the same thing to the entire other side. So we're going to be left with 1.10 to the power of t equals. Now, when I do this division here, let me pull my calculator out and actually check something. Okay. So in my calculator, again, I'm not going to plug the whole thing in there, but I'm going to at least plug in this part. I'm going to plug in 45,950 and divide it by 10,000. Okay. Now, here's where my warning is going to come in. Does everybody see how this has like 3 decimals and doesn't have any more? If this kept going, okay, if this was something really interesting and did something like this, where it just kind of keeps going and going and going, and it has basically like 6 or more decimal places, you would need to write down every single one of these decimal places to not get it wrong. So when you have something like this, I recommend going back and changing it back into a fraction. If it stops like this after like 2 to 3 decimal places and it just stops, then go ahead and you can use the decimal. But if it doesn't, you need to use that kind of weird fraction part, okay? So in our case here, it does stop really nicely, okay? And we have that 4.595, okay? Now, at this point here, I would need to make that conversion. And again, remind yourself that, yes, I know it's got that crazy looking base. It's totally fine to do that base. So we start with our log. I'm trying to write and it's not picking up my writing. Here we go. It just keeps changing it. So log base 1.10. Again, nowhere did I say your base couldn't be a decimal. It just cannot be negative numbers or the number 1. Okay, of that 4.595 equals t. And then now we're going to use a calculator again to kind of plug it back in. So, okay, I'm going to show you guys this in a little bit nicer handwriting there. Again, for those of y'all that have the base feature, you can plug this in the calculator just like that. But for those that don't, you're going to need to go ahead and use that change of base formula, and everybody should got 16. So it's going to take me 16 years if I invest this $10,000 for it to actually grow to 45,950. Okay. Now, please understand that every single one of these problems that we've worked so far have been exponential, meaning that our variable was inside of an exponent. Okay. And these were very nice ones. However, there are some times that we might need to make adjustments, okay? And sometimes they're not as nice as these are, okay? So the format of these are really nice. And so we're gonna look at what happens when it's a little bit different. So we're gonna solve using our log properties now. So solving exponential equations using log properties. We've been doing this, but I do want to kind of keep this in mind This is where when things go a little bit on the wonky side, and I don't want to maybe use log bases. I always want to maybe use natural log or common log, because those are what's in the calculator. This is where these rules will come in. So step one, we're still going to rewrite the equation with the base raised to a power on one side. Again, anything being added, subtracted, it's going to need to go away first. And then if you have a coefficient, go ahead and get rid of that as well. Okay. Once you have done that, step two. So in step two, instead of converting, we're just going to take the log of both sides. Now we're either going to do log or natural log. And again, natural log will be my base E, log will be my common log. And we're going to do that to both sides of the equation. Now, in order to do that, that allows me to use my log property rules, okay? And when I say my log property rules, this is going to be that power rule, that quotient rule, and that product rule that we talked about. And then you're going to solve. Okay, so let's try this out. Okay, I'm going to use the common log just because it's a little bit easier to know log versus ln, unless you rewrite using that ln the way I do. It's sometimes people forget that ln is not in or it's not 1 times something. So what we're going to do is we're going to take this problem, and again, instead of rewriting it as log base 8 of 4,096 equals 2x. I'm going to do this a little bit differently. Okay, so instead of going this route, I'm going to go a slightly different route. Okay, so what we're going to do is we're going to start by just taking the log of both sides. Okay, again, what I do to one side, I can do the same thing to the other. Okay, at this point right here, okay, well, let me pull my power down. So this is going to be the log of that 4,096 equals 2x times the log of 8. Okay, now remember, I am solving for x here, so I'm just going to divide both sides by log of 8. And 2. So I'm dividing by 2 and the log of 8. And there's my answer. I have the exact same answer here. So if you actually take a peek at this here, so this was our old method of using, I would divide by 2, but here's where you would have to use the change of base. So for my TI 83ers, this method is a little bit easier for you. Whereas my TI 84s, you have the log base, this method might be. Okay, so this was the previous method, and this was our new method. You'll get the same answer both ways, so that's really kind of cool about that. But it's just another method, and again, this is going to work a little bit better. I'll put that in there. This one's kind of better for my TI 83 people for the calculator. Or you'll have to take it this route and go, okay, remind myself that this is going to be the log of this divided by the log of this, and then all of that answer divided by 2, which simplifies down to this. Okay. This method here would be better for the TI 84s, minus this part. Okay. Okay. So let me erase all my ink and make it really pretty so you guys can see it there. Again, this is kind of using the power property of logs, which is why that 2x gets to just magically come down. And then as you finish that solving, we have it there. And it's just really nice. Okay. Now, again, your pick, but it's recommended either way. Again, I would recommend this method right here. So for those of y'all that, again, and I know I'm making a lot of reference to higher level math, but for those of y'all that are moving in that direction, if you are going to end up having to take calculus, please use this method, kind of at least explore it a bit, because it is very beneficial, because we use a lot of natural logs when you start working in that, okay? So let's try another problem. So let's solve the following exponential equation. And again, we're going to use that same method. So start first by find your variable. Oh, there it is. It's way up here. And as I begin to look and find my variable, so I found it, it's trapped in the exponent, but I notice the 6. What do I need to get rid of that 6. That 6 has got to go. Okay. And so what I want to do first is I am going to divide both sides by 6. That's going to leave me with that beautiful 4 to the power equals now 120 divided by 6 there is going to give me, well, really nicely, 20. So 120 divided by 6 gives me 20. Okay, and at this point here is where I'm going to go and I'm going to take the log of both sides. And again, I can do log or natural log, your choice, ladies and gentlemen. Again, if you're leaning towards the calculus route, I would strongly encourage the natural log instead. Once I've done that, I can now invoke the power rule. So pull that power rule down. Now I have to be a little cautious here. This power has multiple terms in it. So this is 3x minus 2. All of that is times the log of 4. Okay, and my x is trapped inside of this power parentheses. So I'm going to get rid of that log of 4 first. And I'm going to do that by dividing it to the other side. Because again, why am I dividing? The opposite of multiplication is division. Okay, at this point here, I can solve for x. Treat this just like a big number. So I'm going to start by adding 2 over. So this is going to become plus 2 over here. And then now I can divide by 3. So again, I just divide the whole thing by 3. Okay, as you kind of work it all out, again, I got the same answer, even if I switch it to natural logs. Again, this will be my nice, lovely exact answer. So again, remind yourself, this would be that beautiful exact, and this would be my approximated, my rounded answer. Your choice, again, you'll notice I did this one on the type version with natural logs, but the one that I wrote out on the previous thing, so I'll go back to this slide here. I did it with all common logs. Same thing. Now you'll notice I have this one as the log here is all divided by 1/3. That's the same thing as all divided by 3 is the same thing as multiplying by 1/3. So even if I rewrite this as this way here, I'll get that same answer. We just don't normally keep our stuff written as fractions within fractions. So like a fraction times a fraction is safe, but fractions within fractions. So this would be a little bit nicer to visually see if we write it in like that format, okay, versus this format. But again, we get that exact same answer going this route with the natural logs, okay? Okay, so now let's look at solving logarithmic equations. So what makes these different from what we previously have done? Well, previously, everything we've looked at has been things like 4 to the power of x equals, say, 16, or say 3 times 2 to the power of x minus 5 equals 27. So all of these so far previously have had x in the exponent, making them exponential equations. Whereas the problem that we're currently looking at here, what I notice is that it's a log and x is trapped inside the log. So in our case here, when x is trapped inside the log, instead of us converting to a logarithm, we're going to convert to an exponential. Okay. So with that, what we're going to do is literally go, okay, start by plugging that 4 back up. Okay. So you can either pull the 4 up, or I would strongly actually don't even, it's beautiful x. So instead of putting the power of 4 back up, I'm actually going to divide by 4. So let's divide by 4 on both sides there. So that's going to give me log base 3 of x equals -2. Again, we don't really want anything in front of our log before we do it, because the rule basically says that if I have log base of ry equals x, then that basically becomes our base to the power of x equals y. So you'll notice on this format here, there's nothing being added, subtracted, multiplied, or divided in front of that log. And that's why I want to make sure there's nothing in front first. So either I pull the power of 4 up, or if in my case here, it's really nice, easy if I just divide by 4. That would be a little bit on the better side. Okay, so from there, we're going to write it as an exponential. So again, using that format here. So we start with our base 3 and raise it to the power of -2, and we're going to let it equal x. Well, 3 to the negative 2, I can easily put in the calculator, and which give me 1/9. Now, my deal here, and again, this is very, very important on this one, okay? And I know a lot of people, they're like, oh, I don't have to worry about it. Ladies and gentlemen, we started with a log. I understand we started with a log, but you need to check your answer, okay? When you are in a logarithm problem, all of my answers need to be checked. And the reason being, and let me go ahead and pull up our calculator again and just kind of remind you of a few things, okay? So let me clear out what I have here. If I have, and we'll just use e to the x as a very good answer, idea here. E to the x, when I look at that graph, that domain is all real numbers. It literally goes left forever and goes right forever. Even though it's going up, it's going right forever and ever. So I have a domain of all real numbers. So when I get x equals, it's fair game. No matter what I have, x is probably going to be right. Whereas when we look at, say, a log or a natural log, remind yourself of that graph. Oh, I was limited on the domain, okay? So my domain here was very, very limited. So I always want to make sure that this x value falls within that domain, okay? Now, don't just assume it has to be a positive number. This is where you actually want to take the function that you have, whatever that function might be, and actually graph it and just verify graphically that it does work. So in our case here, yeah, my answer does have like all real numbers that are positive, but just verify that it did work by just kind of plugging in the one side and then -8 and just make sure that it actually does exist. Because if you sometimes it does bring out answers that don't actually exist when you have starting with a log. So anytime that you solve a log, always check. Okay, always check these. I wasn't so big on having to check the exponentials, but these ones we always want to check. Okay, so let's try this again using a slightly different one. So we're going to solve 6 plus 3 times the natural log of x equals 12. And again, when you're looking at these, again, nowhere does it say by converting through exponential form. It literally just says this part right here, solve this, okay? So this is where I have to look at this and go, wait a second, where is x? Once you find x, which again, I found it, it is trapped inside of a natural log. That's what's going to give me my, oh, well, I'm in a natural log and I have basically a really nice way to solve anything that is a log. Okay, and that is the rule that says if I have log base b of y equals x, I can convert to an exponential, which is b to the power of x equals y. So previously we're going from exponential to logs, but now we're going to go from logs to exponentials. Okay, but before I even start, I need to get rid of that 6 first. We're going to take the term that has the log there. Okay, and we need to isolate it. So I'm going to start by subtracting 6. Okay, once I've done that, I am left with 3 times the natural log of x equals 6. Okay, so I've got the term that has it by itself, but now I need to get rid of that 3. So again, I'm just going to divide both sides by 3. So that's going to give me the natural log of x equals 6 divided by 3 is 2. And at this point here, now is when you can use, okay, this part right here is now where I can use this. I cannot use this until I have the natural log by itself, nothing being added, subtracted, or multiplied on the outside. We don't care about the inside. It's the outside that really matters first before I can invoke this rule. Okay, once you have that, now we can invoke the rule. And again, nowhere is this written what base it is, but again, remind yourself that even though it's not written here, natural log is the same thing as log base e. So we basically have e squared equals x, and we're actually done. Okay. Now, again, please be aware that when you look at these in the problems in the book, or if you look at online, a lot of times they don't take that extra step to go, oh, right. Remind yourself that this right here, when I look at it, This is the same thing as saying log base E of X equals 2. If you need to do that, go ahead and do that. It's very helpful for some of you guys that are still trying to learn what natural log and common log have as a base, but just be aware it's not normally shown. It's kind of an understood that you've seen it before, but it's not always easily remembered. Okay, and because I did start with a log in the first place, I am just going to plug the original back in. So again, I'm going to plug this side in Y1 and this side in Y2 and just verify that that is actually the answer. And this is E squared. E squared is actually a 7.38906. Again, this will be my exact answer and that would be my approximated. Okay, let's try again. And again, remind yourself that it does not always tell you what method to use. So again, take a peek at what you have to do. So on this one, I'm going to solve my natural log of X plus 3 equals the natural log of X plus 4. Okay. Now, I want to be a little cautious here. And the reason why, oh, I made a mistake already. The reason why I want to be a little cautious is you'll notice how this was written and how this one was written. It's kind of important to make note of that. Do y'all see how this one here had parentheses and this one didn't? Okay, that's really important to take notice. Okay, why is that so important to take notice? Well, ladies and gentlemen, this one here is different than this one here. Okay, so in the sense there, and I'm going to erase and just kind of rewrite to really kind of give you the idea of what it means. This right here, since there's no parentheses there, it's actually the natural log of X, and then that answer's plus 3 equals the natural log of X plus 4. And that X plus 4 is actually contained in it. This one only contains X, and that's a little bit different. Okay, so we're going to need to use some algebra. Okay, so we're going to use some algebra manipulations to really kind of help us out here. Okay, I'm going to start, okay, and I'm going to walk us through this first. I'm going to start by picking to where I'm going to take this and this because they're both natural logs, and I'm going to make them go on one side of the problem. Okay, so I'm going to subtract my natural log of X. Now, why did I put them on both one side of the problem? Again, when I'm solving these, the only rule I've known so far is if I have log base B of Y equals X, B to the power of X equals Y. So log base B, there's only one log here. And in my case here, I have 2 logs. I wonder if there was a way for me to take 2 different logs and combine them into one. Wasn't there a way that if I had a minus sign between logs, I'm able to combine them into one log? Well, yeah. That would be where it would be 3 equals the natural log of X plus 4 all over X. Again, I'm taking in my quotient rule there. Okay, so I can really use that quotient rule very nicely. Okay, once it's here, now I can invoke this rule. Okay, so again, remind yourself that log is base 3, our natural log there, or is base E, sorry. And so we have E to the 3rd equals the inside. And now we can do our algebra and solve. So we get E to the 3rd times, again, I got to get that X over here. So I'm going to multiply it. Okay. Then I'm just going to move the term that has X over. They both have X. So that means I'm going to factor out an X. And I'm going to be left with 4 divided by E to the 3rd minus 1. And there we go. Okay, again, keep in mind why we did this was because I need to have it as 1 log. Okay, this rule only applies 1 log equal a number. So log equal number, then you can do this. But again, if it doesn't equal that number, we have to kind of maybe manipulate it using some algebraic or log rules to help me out. Okay, let's look at a word problem because we haven't seen a word problem in a second. So in an effort to reduce global warming, it has been proposed that a tax be levied based on the emission of carbon dioxide in the atmosphere. Now, the cost-benefit equation that we have is the natural log of 1 minus p, and again, that's the natural log of the entire 1 minus p, equals a negative 0.0034 minus 0.0053t. And it estimates the relationship between the percent of reduction of emissions of our carbon dioxide, which is p, which is given to us as a decimal when we work our problem out, and the tax, T dollars, in dollars per tons of carbon. Okay, so what exactly do I want to do? Well, in part A, I want to take that equation and actually solve it for P. Okay, so I want to take this equation here, our natural log of 1 minus P equals our negative 0.0034 minus 0.0053T, and I want to solve for P. So let's start by just finding, where is P? It's here. And let's look at what's surrounding P. Okay, so as I notice here, P is inside of a natural log. So since it's inside of a natural log, I might need to do a little bit of tweaking here. Okay, so this is where, when we take this, again, I'm going to write this up. I don't know how many times I've written it down. It's been a bit. So keep in mind that when we look at the formula, we're going from log of some base, okay, to an exponential, which is going to be that base to the power. Now, my power is everything that's on this side. So in our case here, what we started with, remind yourself, we started with the natural log of 1 minus p equals a bunch of stuff, right? So when I do this, all of this stuff over here is now going to become the exponent, okay? So in our case here, please understand that this is still going to stay 1 minus p because that's what was inside of our log, but this is going to be e to this entire other side here. And then all I have to do is basically, you know, add p over here and then subtract this, and then we have our answer. Works out, right? But again, remind yourself that when we do this, all of this stuff is what x is representing. X here in our problem, and that's where a lot of people forget. X is at, this is in general terms, X can be a bunch of stuff. And in our case, it's a bunch of stuff. So all that stuff gets to become the exponent. Okay. So now that I have it in P equals, our function is basically our P, which is our percent of reduction of emissions in terms of tax dollars per ton of carbon. Let's look at what if I give you a second part to it. So let's determine the estimated percent reduction in emissions if the tax of $100 per ton is levied. So in our case here, all I would need to do is plug in 100. Now, since I'm plugging in 100, again, I'm only plugging in 100 in for T. So let me go and pull my calculator back up, plug it in. Okay, I've already done the math for us here. So I've plugged it in. Again, those of y'all that have a TI-83, be very aware that this is not going to show up as an exponent up here. It's just going to be using the caret symbol. Make sure that there's parentheses around that entire exponent, the whole thing as one big item. Now remember, P was given in a decimal, and the question is asking what is the percent. So I do need to change this to a percentage. And one of the things that we have with this one is it doesn't actually have a percent button in this calculator. So I just need to multiply by 100 and I'm able to get that. Okay. And that basically gives me my answer of 41.3%. Okay. Let's try again. Woohoo. Again, I know you guys are not very fond of word problems, but don't let word problems mess you up, especially if they already give you a formula in them. So in our case here, after the end of an advertising campaign, the daily sales of Genepets fell rapidly, with daily sales given by S equals 3,200 times e to the power of a negative 0.08x dollars, where x is the number of days from the end of the campaign. for how many days after the campaign ends were the sales at least 1,980? Okay, so as we work our way through this problem, the first thing I want to remind myself is that I've got a beautiful formula, right? It's gorgeous, it's right there. And I want to know in how many days, well, remember we just said X is a number of days, so that means we're solving for X, were the sales at least 1,980, okay? So let's start by just plugging in. We need to find where it is 1,980, okay? Now this is where we're going to use that method that we looked at the very, very beginning. So remind yourself, E and X is in an exponent here. So let's start by getting rid of that 3,200, okay? And then I'm going to convert it into a logarithm. So I'm going to have that natural log of E. Again, I'm going to just take the natural log of both sides. That works just as well. And what happens when we do the natural log of E on this side is just going to give us our beautiful exponent there. Okay. And again, the natural log of that number is this. And then I'm just going to divide by a negative 0.08, which means it's approximately 6. Now, again, I could have also used a ability to use the graphing calculator, and that would work just as well. Okay. So for how many days after the campaign ends were the sales at least 1,980? Basically, at least this amount would be about 6 days or later. So like 6 and beyond. It's going to be at least 1,980. Okay. Let's try again with a lovely formula already given to us. So we looked at this one already. Again, so the cost benefit equation of our natural log of 1 minus P here equals a negative 0.0034 minus 0.0053T. And again, that estimates the percent reduction of emissions of our carbon dioxide P. Again, that will be that percent is given to us as a decimal in the problem itself. And the T being the tax dollars per ton of carbon. So what tax will be given for the reduction of at least 50%? Okay, everybody see the word where it says tax? What tax? So that means I need to find T this time. So I'm solving for this, which means they gave me P. Now remind yourself, it says at least 50%. So in order to make this work, we need to start by basically changing my 50% into a decimal. So everybody remember 0.50, plug that in, and then solve. Okay. Now the cool thing is as I'm plugging that in and we're solving for T here, once I plug in this, realistically, T is not in. Again, take a peek. T is not in an exponent. T is not inside of a log. So this is just going to become a very basic back to linear problem because once I plug in, and I'll show you my math here. Once I plug in this, I can plug this into the calculator, get an answer, and now it's just a very linear style problem. So remind yourself, you don't always have to be using or converting between logs and natural logs. It's just going to really kind of depend on the problems when we look at them to really see whether or not I need to use them. In our case here, once I plug in 0.5, I didn't have to go solving for the P because it wasn't trapped inside of the natural log anymore because I plugged in the number and T is not trapped as an exponent. So there's not other than just basic algebra now of let me go ahead and add this over to this side. Okay, combine these two numbers, which is going to give me that 0.6897. And then we've got it equal to our T. I need to get rid of that coefficient. So I'm going to divide by that coefficient and you should get our T equals 130.14. So basically that tells me that if the percent is going to be, if we have at least 50% tax reduction, then I need to really have above $130.14 to actually per ton of carbon to really make that beneficial. Okay. Now, again, you'll notice my answer is above. So again, it's not just this number, but it's this number and above that to makes it more beneficial for that P being that 0.5. So it said at least here, so I said that or above for that. Okay, as you guys continue to work on these, definitely make sure to write down all the formulas. There's a lot of formulas in this, and I really suggest that you refer back to your notes from previous sections for the formulas and really practice them, because as you can see, they're kind of used in the solving problems.